my name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on AQA rate equations. So this video is specifically designed for AQA, so if you're studying AQA A-level chemistry, then this video is perfect for you. It contains everything you need to know and nothing more. So it's not like other resources where you may see, particularly online, where you may see them as generic and they might have generic information in there and you're not sure if it's for your board or not. Well, these videos are specifically designed for you. So if you are studying AQA chemistry, then this is perfect. And indeed, there is a full range of AQA videos from year 1 and year 2 that cover specifically this syllabus, as well as some general whiteboard tutorials as well, looking at specific areas in a little bit more detail, and also we've done some exam walkthroughs as well, some past papers to make sure that you improve your exam technique. It's all for free. All I ask is that you hit the subscribe button, and that would be completely fine with me. As long as people keep subscribing and people keep watching the videos, then I will keep making them. So please hit the subscribe button. That would be brilliant. It just keeps the whole thing alive, really. Also, if you would like to, this is just a PowerPoint slide that I've created, but if you would like a copy of the PowerPoint slide, they are available to purchase. If you just click on the link in the description box, you can get them from my TES shop. They're great value for money. There's got loads of information, as you're going to see. Ideal for revision. You can use it on your smartphone or PowerPoint smartphone or tablet. You can even print them off and use them as part of your revision notes if you like. So there's loads of information on there, but if you just click on the link in the description box, and you can get a hold of them there. Okay, so like I say, this is dedicated to AQA and it meets the specification points on here. And so the main topics that we're going to discuss are things like rate equations, and we're going to look at rate equations, and we're going to look at the experiments. For example, we're going to look at experimentations such as how to measure rate of reaction using the equipment and plotting graphs. And we're also going to look at the Arrhenius Equation as well. So that should be exciting. If you've ever seen the Arrhenius Equation, it looks horrendous. But hopefully this video is going to make it a lot simpler. That's what I aim to do. So right, okay. So let's start with calculating rate from a graph. So when we do rates of reaction, obviously we'll look at the practical side of it later, looking at the equipment we use, but when we do a rate of reaction, we obviously need to plot results from that. We're monitoring how quick something happens. So from that, we'll have to be able to plot graphs from the results that we get, and then from that graphs, we can then work out the rate. So this is going to look at how we can calculate that rate from the graph. So rate can be found from the gradient of a graph. So you can see here that we've got a rate equation. We've got a rate graph. We've got volume of gas produced in centimeters cubed up the left-hand side, and then we've got time at the bottom. So everything in here, everything on here, you might have seen before from year 1, but we're just building upon that. We're just developing your knowledge from year 1 chemistry and just adding extra bits to it. So quite simply, to work out the gradient, we do change in y over change in x. So remember, y is the axis down here, that's on the left hand side where you can see my cursor, and then on the right hand side, coming across here is the change in x. So the bigger the section of the graph you use to work out the gradient, the better. Now you might have been told from your teacher. I know when I was teaching in schools, one of the things I would say, to a lot of students is when you're drawing a graph, is you make sure it's at least half the graph paper, because if it's smaller than that, it's really difficult to read from a graph that's tiny and squashed up in the bottom. So always, as a general rule, at least half the graph paper, and particularly when you're working out a gradient, you try and get the biggest gradient you possibly can, the biggest section to work out the gradient from your graph, because if you do it that way, it means you're more likely to get results which are more accurate and reflect your results from your experiment more carefully. So what we're going to do is we're going to try and find points on the graph where the change in y and change in x can be worked out really easily. So let's have a look on here. So we've drawn our gradient lines on here, and we can see if we put the numbers in, we've got 6 on the x-axis, and the change in y is going to be 4. So that's all we do, and basically we put them into our calculation and we work out the gradient, and so the gradient is going to be 0.67 centimeters cubed per minute. Now the units are interesting here actually, because the units are, I don't mean if you may already know this already, but units, if you don't, because there'll be some people who may not be quite as good as maths as others, but the units are worked out quite simply, where we take centimeters cubed, we take the units from the y-axis and the units from the x-axis, and we just write it there. So it's centimeters cubed per minute. So that's where we get the units from. So just look at your x and y-axis, and that tells you what your units are going to be. Okay, so what if our graph is actually a curve? So the graph that we've seen there is a straight line graph, but you can also get curved graphs as well. So all we do is we use a tangent. Okay, so again, if you do maths, you'll know exactly what a tangent is. If you don't, then for those who don't, then a tangent is just a diagonal line that meets a curve at a specific point. Okay, so and all we do is we extend that line right across the graph. Again, the biggest gradient we can get, the biggest marked gradient we can get, and then what we do is we use that gradient to effectively work out the rate of reaction at a specific point on the curve. So let's have a look. So you see we've got the curve graph here. And you can see we've got the mass of reaction vessel is in grams, and we've got the time in minutes towards the bottom. So in this example, what we're going to do is we're going to work out the rate of reaction at 3 minutes. So there it is there. So we draw a tangent, it strikes the curve at 3 minutes, as you can see. So there's 3 minutes there. And so if we go up, you can see it just strikes the curve at that point. So that's the tangent we're going to use. And then the gradient is just a change in y over change in x. It's exactly the same as what we were doing last time, except we're going to do it on the tangent that we've just drawn. So let's work out the numbers. So there's our gradient markers. And so we've got 0.8 on the y-axis for change in y. And then change in x is going to be 4, as you can see there. So we put all that into our equation, and we get a gradient of 0.2 grams per minute. Again, it's grams per minute because we've got grams on the y-axis, as you can see over here, and we've got minutes on the x-axis, as you can see down there. Okay, so we're going to look at the rate equation, and we're going to look at something called orders. Now, effectively, the rate equation just links the rate with concentrations of substances, and some of them concentrations have orders as well, and we'll look at what orders mean in a moment. So let's look at what this looks like. So rate equation is rate equals K, which is a rate constant. We'll look at that in a moment. And you've got concentration of A, concentration of B. So that depends on the reactants and the reaction that we're actually looking at. And you can see the superscripts or the indices at the top here as well. So you've got A and B. These are something called orders, but we'll look at that in a moment. So just again, rate is done in moles per decimeters cubed per second. So that's the rate of reaction. K is your rate constant, and the units vary, so you need to be able to work them out, and we'll look at how you can calculate them as well. B is the concentration of a substance. So for example, in the following equation, you do A plus B gives C plus D, so A and B is just the reagents that we're using, or it could be a catalyst as well. You can have catalysts in there. And the little indices at the top are what we call orders of reaction, so we'll look at them as well. Okay, so orders of reaction is the power to which the concentration is raised to in the rate equation, and it basically tells us how the concentration of the substance affects the rate. So, for example, you might have we have zero order, first order, and second order. And so what we'll look at now is what the different orders are and what they mean in relation to concentration, change in the concentration, and change in rate. So a zero order is where if we change the concentration of a substance, then it has no effect on rate. So in other words, if we double the concentration of A, then rate doesn't change. Now, if you're in industry and you're wanting to make a reaction and you're wanting to make it quickly because it's time is money, as they say, then there's no point in you doubling the concentration of a substance if it's going to have no impact on rate. So actually knowing what the impact is of concentration and rate is quite powerful. So first order is changes in concentration. Any changes in concentration is proportional to the change on the rate of reaction. So for example, if we double the concentration of A, then the rate doubles as well. So that could be quite useful because it means if we can double A, we get a faster rate. So that could be quite useful in industry, in particular if we're wanting to make a substance, then we know if a substance has an impact on rate, if we double that, then we can make it faster. So that's quite useful as well. Okay, the last one is second order, and second order is where changes in concentration has a squared proportional change on rate. So for example, if the concentration of A doubles, then the rate quadruples. So this has a disproportionate effect on rate, is a second order reaction. Now, remember, orders can only be determined by experiment, okay? So we can't work them out just by looking at equations. So I can't look at an equation that's written down in front of me and tell you, what impact this reagent would have on rate. It's just impossible. You have to actually do the practical, get your graph, plot your graph, and then work out the rate equation from that and see what impact changing the different reagents are on rate. So that's very important. We'll look at some data in a minute later on, where we have some data and we're trying to work out the rate of reaction, because actually in the exam, because you can only work it out practically, the exam board have to give you the data to work this out, because you can't just look at a reaction and work it out. So as soon as you see this type of data, you'll know what to do with it, and we'll look at that later anyway. Okay, so we're going to look at the rate equation. Still stay on the rate equation, but the rate equation links rate with concentrations of substances, as we know. But what we're going to look at is look at some more of the different elements of the rate equation, such as the rate constant. So the rate constant is given the letter K. Yep, so they give it rate constant K. I don't know where they've made the link with that is. Anyway, but it is K. And a constant is a number that allows us to equate rate and concentration together. So the rate constant is only fixed at a particular temperature. Okay, so it doesn't actually stay fixed in all conditions. So it is temperature dependent. So if the temperature changes, so does the rate constant. Okay, so K increases when the temperature increases as well. So the larger the value of K, the faster the rate of reaction. That kind of makes sense, because if we increase the temperature, the value of K increases, and if the value of K increases, that means the reaction rate has got to be faster, because the particles have got more kinetic energy, and so that means they've got a higher chance of successful collisions. So the explanation part, why does this happen? So when you think, if we increase the temperature, the particles have more kinetic energy, as I said, and this means they collide more often, so therefore the rate increases. So if we bring up our rate equation, as you can see there, rate is this element here, so it's on this side. Now, the concentrations of the substances, A and B, as you can see, remain the same. It doesn't matter if we, really heat this reaction up. The concentrations of the substances aren't going to change, so they remain constant. So to balance this equation out, we must have K increasing to make it equal the rate. So there we are. So that must increase as the rate increases, and the rate will increase if the temperatures increase. So that's how we can make these links between temperature, rate, and the rate constant K. That's how we can make them links. Okay, so let's look and see how we can calculate the rate of reaction. So rate can be calculated using the rate equation that we've just seen there. It's a fairly straightforward one to use, actually. So let's look at this example. So we've got the following reaction was carried out in a lab. So we've got 2NO plus O2 will form 2NO2. Okay, it was found that the reaction is second order with respect to NO and first order with respect to O2. Calculate the rate of reaction given the concentration of NO is 3 times 10 to the minus 3 and O2 is 1 times by 10 to the minus 3. The rate constant K has a value of 700,000 moles to the minus 2 dm6 s to the minus 1. Okay, so we've got a lot of information there. Remember, we're going to be using our rate equation to work this out. So write the rate expression first. So the rate equals K NO squared O2 1. Now what I've done is we've taken the elements here because we know what orders they are with respect with, so we know it's second and first order, and we've written our rate expression showing these different substances here. Now you can see we've got a squared bit here. The squared bit is the concentration of NO, and then O2 as a power of 1. Normally we don't put the power of 1 in there, it's just to show you that this is first order. So normally with this you just get rid of the 1 bit, you get rid of that completely and you're just left with O2. So then we substitute the numbers in there. So we've got the rate, and we know that the rate constant K is 700,000 moles to the minus 2 dm6 s to the minus 1. So we know that. And multiply that by the concentration of NO, which is 3 times 10 to the minus, where was it? There we are, 3 times 10 to the minus 3. That's squared, because we've got two of them, it's second order. And then times by 1 times 10 to the minus 3, which is the concentration of O2. So put all them numbers in, and we get the rate, which is 6.3 times by 10 to the minus 3 moles per decimeter cubed per second. Okay, so the units for rate are always that. Okay, so there's no variation. Units only change when we're looking at the rate, the rate constant, sorry, which is K. Okay. So let's look at the rate constant. So we can actually calculate that as well. Obviously, we have to do a little bit more rearranging for rate constants. Obviously, the rate of reaction is fairly straightforward to work out, but rate constant is a little bit more difficult. So again, let's look at this reaction this time. So we've got a following reaction carried out in a lab. So we've got nitrogen monoxide reacting with carbon monoxide, reacting with oxygen, and that produces nitrogen dioxide and carbon dioxide. So we need to calculate the rate constant for this reaction, given the order with respect to NO is second order, and zero order with respect to carbon monoxide and oxygen. So the reaction of all reactants is the same, so it's 1.5 times by 10 to the minus 3 moles per decimeters cubed, and the rate of reaction is 1.17 times by 10 to the minus 3. So the first thing we need to do is write out our rate expression. Now notice here, we've only got NO in this rate expression. Carbon monoxide and oxygen do not appear in the rate expression because they have zero order. They don't have, changing the concentrations of them have no effect on rate, so we don't put them in the rate equation. So the only one that we put in there is NO, and because it's second order, we put the little 2 as an indice at the top there. Okay. So then we need to rearrange it to work out K. So we rearrange to make K the subject. So K equals rate over the concentration of NO squared. And then we chuck our numbers in. So rate is 1.17 times 10 to the minus 3. The concentration of NO is 1.5 times 10 to the minus 3 squared. Put all that in and we get the value of K, which is 520. Now, remember we said the rate units of rate are the same, whatever conditions it's in, but K isn't, and we need to work out the units of K. Okay, it's really straightforward to work that out. All we have to do is write the units of rate on the top and then concentration twice on the bottom. So like this. Okay, so we substitute, instead of having the letters here, we put the units of each of them. So K, the units for K is moles per decimeters cubed per second, and the units for nitrogen monoxide, the concentration of, is moles per dm cubed. We write them twice because we've got a squared function there, so we must write them twice on there. And very simply, we just cross out the units top and bottom. And then once we've crossed them out and cancelled them out, we then invert any that's left over on the bottom. We invert them, put them onto the top, and we change the sign. So instead of mol, it's mol to the minus 1. And instead of dm to the minus 3, it's going to be dm3. So you'll see. There we are. So we cancel them out and we invert them. We flip them up. So the final unit should be mol to the minus 1, dm3, s to the minus 1. So fairly straightforward, not too bad, not too traumatic. Okay, so initial rate, okay, can be found too using the gradient of a tangent. So initial rate is just the rate right at the start of the reaction. So unlike the previous example where we worked out the rate at, I think it was 3 minutes, I think we worked it out at, this one we're going to work out the rate right at the start of the reaction. So just like what we've done before, we take the gradient of the tangent on this curved line, but we take the tangent at 0 minutes. Okay, so the tangent at 0 minutes is going to be something like this. Okay, so that's your tangent. And so the gradient is going to be change in y over change in x, just like we've done before. So let's work out the difference in y. It's going to be 1.7, and the change in x is going to be 1. Okay, so then if we put all the numbers into the equation, we get a gradient of 1.70, and this is grams per minute. Again, we know it's grams per minute because the y-axis is in grams and the x-axis is in minutes. So it's, again, fairly straightforward, but the only difference is we have to take it at 0 minutes because we're working out an initial rate method. Okay, so why do we use initial rates? Well, initial rates are so important because we can work out the rate equation of a reaction using the initial rates method. So let's say we want to work out the rate equation for A plus B plus C will give D plus E. Okay, it's a generic equation. So remember, we can only work out the rate equation by conducting an experiment. That's the only way we can do that. Okay, so repeat the experiments. So what we do with this type of with the initial rates method is basically we repeat the experiments several times, but changing the concentrations of A, B, and C one at a time in each experiment. So what we want to do is find out the effects of changing each one on rates. So in other words, we change the concentration of A, but we keep B and C the same. Then we change the concentration of B, but keep A and C the same. And then we change the concentrations of C and keep A and B the same. So we're just changing one at a time, and we're seeing, does each of these have any impact on the rate of the reaction? Okay, so we need to work out the initial rate for each experiment, and we calculate this using the graph shown below. Okay, so we've done all that. And so then once we've done that, we then need to record the concentrations of reactants used for each experiment and their initial rates. We need to record them in a table. And then from this, what we can then do is work out the orders with respect to each reactant, and then we write out our rate equation. Okay, so that's the practical side. That's how you would do it in a laboratory. Okay, so let's have a look at this practically in terms of the table. So here, for example, we've got experimental data for the following reaction. So we've reacted nitrogen monoxide, 2 moles of nitrogen monoxide reacting with chlorine, and that's going to form 2NOCl gas. Okay, so we're forming that product. So we need to give the rate equation and calculate the initial rate for experiment 4. Okay, so you can see here we've got the data. So we've worked out we're using this information with the concentration of NO, the concentration of Cl2. We've plotted it on a graph and calculated the initial rate of each one of these, and we've worked it out there. So this is going to be in moles per decimeters cubed per second, and we've worked out the initial rate by doing these experiments. But we don't have the initial rate for experiment 4, so we need to calculate that. So first of all, we need to work out the order with respect to NO, and ideally, you just need to compare the experiments where the concentration of NO is changing and the concentration of chlorine is remaining constant. So we can see this one here and this one here. These two allow us to compare. So we can see the concentration of NO is increasing and the concentration of Cl2, you can see, is remaining the same in each of these. So any change in rate is going to be caused by NO and not caused by chlorine because we're keeping that the same. So you can see here, experiments 1 and 3, NO has quadrupled, it's multiplied by 4, and so has the rate. The rate has quadrupled as well. So the order with respect to NO is first order because it's directly proportional to it. Okay, so secondly, what we need to do is work out the order with respect to Cl2. And ideally, again, we need to compare experiments where chlorine is changing, but the concentration of NO is remaining constant. So the examples we can use here is number 1 and number 2, because the concentration of NO, as you can see, isn't changing here, but the concentration of chlorine is. So any change in rate is going to be caused by chlorine and not by nitrogen monoxide. So you can see that chlorine has trebled, the concentration of chlorine has trebled, and the initial rate has trebled as well, so that's increased by 3. So the order with respect to chlorine is also first order. So once we've got that, we can now work out our rate equation, and our rate equation is rate equals K, concentration of NO, and the concentration of Cl2. So pretty straightforward, as you can see, and obviously we haven't put the ones on next to each of the brackets there because obviously we know it's first order, so we don't need to put the ones there, and we just keep it the same, but yeah. Okay, so remember that the rate equation is this, and we still need to carry on going because we need to work out the initial rate of experiment 4. So first of all, what we need to do is calculate K. So this is straightforward. All we do is just pick any experiment where all the data is complete. K is the same value for all experiments in this table because it's all at the same temperature. So let's have a look. We'll just pick one of them. Let's pick experiment 1. And using the data in experiment 1, we're going to put all the numbers in there and work out K. So we've got rate equals K, concentration of NO, concentration of Cl2. We rearrange that to make K the subject. So K equals rate over NoCl2. K, put the numbers in, and K equals 31.5 mol to the minus 1 dm cubed S to the minus 1. Okay, so this is the units for K. So we've worked out K. Now we've done this, we can then literally use the rate equation and the value of K to calculate the rate in experiment 4. Okay, so we've put in the rate equation, rate equals K, NO and Cl2. We've put all the numbers in, including the value of K that we've just worked out there, and then we should get a rate of 7.88 moles per decimeters cubed per second. And so that's how you'd work out, obviously, the missing data here for the rate, the initial rate. Pretty straightforward. There's a lot of steps there. So in summary, what you need to do is you need to work out your orders first. Then once you've worked out your orders, you write down your rate expression. Once you've got your rate expression, you work out K. And then once you've got K, you then use that to obviously rearrange the formula to, well, it depends what you're working out, but in this case we're working out rate, so we don't have to rearrange it, but we use K to work out the rate for the unknown reaction. So there's a few steps there, but quite a few marks you'd get. Okay, this is a tough one. This is a difficult one. They might give you one of these because they'd be quite mean. So this is the initial rates method, but a much more difficult example. And this is where actually we get a set of data in the table that doesn't have a substance where the concentration remains constant. So in them ones, it was all right because we had one of them was remaining constant and the other one was changing. Sometimes you would never do it practically like this. Clearly, they're just testing your knowledge and your ability to interpret the data. That's what they're testing you on. But in theory, you wouldn't set it up like this. You would always keep one the same and change everything else. It makes it a lot easier. But this is an example where it's not going to happen. So I've got a particular method for this one, and the method is to basically extend the table and add an extra column. Now it might be the case that you might have a different method. If you've seen any of my other videos, I like to keep things methodical and keep it all nice and neat and tidy and see exactly what's going on. And it means if I've made a mistake, I can then go back and check and make sure it's right. And also for your benefit as well, because what you need to be able to do is demonstrate to the examiner you're working your methodology. So if I go through it in that way and then you imitate what I'm doing, then it means that you're likely to get the marks that you deserve to get if you're showing you're working. So this is my method. You might have a different method of doing it. It works well, and it's nice and neat. So it's up to you whether you follow the method, but the principles, obviously, you need to be able to apply in your exam. So let's have a look. We've got a reaction that occurs between A and B, and the experiment was repeated 3 times, varying the concentrations of A and B. Give the rate equation for this reaction using the data below. Okay, so what we've got is 3 different reactions. So we've got the concentration of A and B, and we've got the initial rate, and we've repeated the experiment varying the concentrations of A and B, and we've repeated the experiment 3 times. So firstly, what we need to do is work out order with respect to A. Okay, so that's the first reagent. So ideally, we need to compare experiments where A is changing and B is remaining constant. So let's have a look. So here we can use experiments 1 and 2 here. So A has trebled, so that's increased by 3, and the initial rate has increased by 9. So that means that the order with respect to A is second order. So you can see here that the concentration of B is remaining the same, the concentration of A is changing, so that means our initial rates, an effect here, is only because of A and not because of B, because we know B is remaining the same. Okay, so secondly, what we now need to do is work out the order with respect to B. Now, this is tricky because A changes in each experiment. So you can see here that there isn't a single experiment where A is remaining constant. So all of these are actually different. So that's really difficult to actually nail down which one to use for B. So what we need to do is we add another column at the end showing what the rate would be if we only changed A. Okay, so looking at experiments 2 and 3, okay, so looking at these ones, we can see that concentration of A doubles, so this doubles, so the rate must quadruple, as we know it's second order with respect to A. So this gives us this rate. So basically what we're doing is we're just ignoring B, just pretend B never existed. We know the order for A because we've just worked it out, and we know it's second order. So if we double this, then the rate would quadruple. So what we do is we write down what that rate would be in a next column, add an extra column onto the end, and we write it down here. So this is the theoretical value. And what we're going to do is we're then going to compare this value to what is actually the rate. And we can see there is a difference. So what that's telling us is that B must have an impact on rate. It must do, because the figures aren't the same. If these numbers were the same here, then we can say that B is zero order. Okay, but it isn't. It's going to be different. So finally, what we have to do is we have to obviously spot that difference. We can see it does have an effect, and we can see it is about half. So this is caused by halving B. Okay, so B, remember, has gone from 24 to 12. Okay, to 0.24 to 0.12. So that's halved. So that means that the rate has also halved. So that means that it is first order with respect to B, and that's basically how we work it out. Okay, so it's about adding that extra column on the end and comparing it with the actual value that you've got. So the rate equation is rate equals K, A squared, and B. Okay. So you can see you might have a slightly different method, you might have a completely different method, but as long as you get the same answer, that's fine. You've got to be able to demonstrate that to the examiner as well. You've got to be able to show how you've worked that out. Okay, so we're going to look at something called an iodine clock reaction, which is a really nice reaction because it literally changes colour over a specific time period. It's quite a nice one. So this is a reaction, like I say, where we can time how long it takes for a colour change to occur. Okay, so you might have done this at GCSE with sodium thiosulfate reactions, for example. So you might have done this already. You might have done it at A level as well. You might have done the practical. So this one is an iodine clock reaction, and effectively you've got peroxide, hydrogen peroxide, in acid and iodide ions, and that's reacting to form iodine, which is I2. So all we do is we add sodium thiosulfate and starch, which is an indicator because it will react with the iodine and turns a pitch black colour. It's like a dark blue black colour. And we add that to the reaction mixture, and so the sodium thiosulfate actually reacts immediately with the iodine that is produced in this reaction. So we produce the iodine, the thiosulfate reacts with the iodine immediately. And so when there is no more sodium thiosulfate left, then the iodine reacts with the starch. Okay, and this gives this deep blue black colour like I suggested before. So as the sodium thiosulfate is added to this reaction, it reacts with the iodine, which is on here, and then once all the sodium thiosulfate has reacted and there's no more left, if we have an excess of iodine, then the iodine will then turn its attention and react with the starch, and you get this bluey black colour. So what this means is by varying the concentration of iodine, okay, so I2 and or hydrogen peroxide, and keeping everything else constant, what that will do is result in the time taken for the blue-black colour to appear and changing. So and we can use this to work out the order of the reaction. So it's quite a useful experiment in terms of working out order. Okay, so reactions like the iodine clock, these can be monitored by sitting a reaction vessel on some paper with a cross on it. So this is this method might be quite familiar to you, and we basically time how long it takes for the cross to disappear. So we basically look down the top of the flask. We have our paper underneath with a cross. We look down the top of the flask, and we wait until this colour, effectively either we form a precipitate, or obviously in this case it's going to be iodine turning black because of the starch that's added to it. So, and we stop the stop clock once once it goes black, and we can alter the concentration, like I say, of iodine and peroxide in here, and that's obviously going to have an impact on the rate of reaction. So if we increase the concentration depending on the order, then see if that has an impact on the time it takes for that cross to disappear. Okay, so let's have a look at what other ways we can measure rate in experiments. Obviously, that's one way, which is the iodine clock experiment, whereby we obviously using iodine and sodium thiosulfate to actually time the rate of reaction using disappearing cross. But we can also do it with a change in pH as well in a reaction. So the pH of reaction may change over time if the concentration of H plus ions are used up or produced. So a pH meter can be used to measure the pH of a reaction at regular intervals, and then we can calculate the H plus ion concentration. So basically, what we're doing is we are allowing a reaction to proceed, and at regular time intervals we're taking the pH of it and seeing how the pH changes. Another one is amount of mass loss, which you would have seen a graph for already. So basically you have a top pan balance, and we have our beaker or conical flask with our reaction going on inside there. And this is suitable for reactions that produce a gas, because these gases can escape from the reaction vessel, and effectively the loss of mass over time can be measured. So for example, if there's a large mass loss at the start, you can say that the rate of reaction is quick, and then if the mass loss decreases over time, then you can see that it's slowing down over time. So we can do what we call mole calculations. Obviously you would have seen mole calculations in year one. So do mole calculations can be used to work out the number of moles of gas lost, and hence we can work out the amount of reactants left. So we can use mole calculations to monitor that. Okay, so volume of gas produced is another one. This is an interesting one. So you have a reaction vessel that is producing gas, but instead of just letting the gas escape, we're actually trapping the gas in a syringe and monitoring how much gas is produced per unit time. So this is an interesting one, because if you get your reaction mixture wrong, or you mix it in the wrong quantities, sometimes you can produce too much gas, and effectively the plunger of the syringe flies off the other side, which is not helpful. So you have to make sure that obviously the reaction that we're using here is going to be suitable for this type of equipment. So the ideal gas equation, which you would have seen in year one chemistry, so this can be used to work out the number of moles of gas produced, and then we use the molar ratio on the equation to work out the reactant concentrations. Okay, so like I say, if reaction has a colour change, this can be measured using a colorimeter. So we looked at one of the ways in which you can measure a colour change, and that's using the disappearing cross reaction. But the problem with that is it's quite subjective, in the sense that you look down and, how do you know exactly the time when that cross disappears? It might be a gradual disappearance of the cross. One person's complete disappearance of the cross is another person's partial disappearance of the cross. So it's really difficult to get an accurate time or decision on when it actually disappears. It helps if you use the same person to look at it, because then they're taking the same subjective view. But using different people, it's going to confuse your results. So what we can do is we can use a different method, which is a colorimeter, and it's a better method to use. So a colorimeter looks a little bit like this. You may have them in school or college, you might do. But a colorimeter, all that does is it measures the absorbance of light off a coloured sample. Okay, so the more concentrated the sample, the darker it is, and hence the more light is actually absorbed. So this could be useful, particularly with reactions where we're producing, say, a colour which is getting darker over time. We can monitor the absorbance over time, or it might be getting lighter. It depends on what type of reaction you're doing. So this could be quite useful for chemicals where the colour is changing over time. So a classic example here is a reaction between propanone and iodine. So we can see here the reaction goes from brown to colourless. So your iodine is brown, so it'll start off brown, and as the reaction proceeds, it will become colourless. Now, this colourless solution may appear quite quickly initially, which means that you've got quite a quick, large rate of reaction, so a fast rate of reaction. Or it may actually appear quite slowly. You've got a slower rate of reaction. So this reaction here is a classic example of when you could use colorimetry because you've got a colour change. So when we're doing colorimetry, the first thing we have to do is actually plot a calibration curve, and it's created by making up a range of known different concentrations of iodine for this particular example. And then what we do is we measure the absorbance of each one and we plot the results. So this gives us a benchmark. So if we plot the concentrations of iodine, as you can see on there, at regular points. We measure the absorbance. And then an experiment like the one above is set away, and samples are actually taken regularly from this. And these samples are then tested for absorbance. So we take regular amounts from it. And then what we do is we then use this calibration curve that we've created and absorbance, and we find out the concentration of iodine. So what we do is we look at the sample that we've got, we stop it at a particular time point, and then what we can do is measure the absorbance, because we measure the absorbance from the test tube. Once we know the absorbance, we can use the calibration graph to then work out the concentration of iodine at that point. So it's quite a useful tool to measure the concentration of iodine, but you do need to make standard solutions at fixed concentrations, measure the absorbance to be able to do that in the first place. So it is a little bit time consuming. Okay, so what we're going to look at are rate concentration graphs. Okay, so these can help us to identify order. Now, what we looked at before was concentration time graphs. They're the graphs that we use straight from practical technique. So we use a practical, we carry out practical, we take the concentration over time, we plot the results, and we take a gradient. And the gradient will tell us the rate of reaction. Now, what we can do is we can work out the rate of reaction, say across the curve or the line, take the rate for each of them and plot this against time instead. Now what you need to be able to do is identify the shapes of these graphs and then link that with an order. Is it 0, first or second order? So this is what we're going to look at here, but you mustn't get confused between these graphs. So let's have a look. So a rate concentration graph is created by knowing the rate, like I said. So you take the rate across your graph. And that's obviously found from the gradient at various points on the graph. So we don't want to get these mixed up. So let's have a look at the first one here. So the rate on a straight line graph is constant. And so the rate concentration graph shows a horizontal line. So changing the concentration doesn't change the rate of reaction. So this is 0 order. So look at the difference. This is what you plot from your practical data. So concentration over time. And then we take the gradient at each one of these to find out the rate of reaction, and then we plot rate against concentration, and if we get a straight line on this graph, this symbolizes a 0 order reaction. So rate on a shallow curve graph changes in equal amounts. So the rate concentration graph shows a straight diagonal line, and changing the concentration changes the rate. So this is a first order, so it changes it equally. So you can see here, if we take the gradient, or the tangent, should we say, across various points on this curve here, okay, and then we take the rates of each of them, that's the gradient, and we take them rates and plot that against concentration, and we get a straight line, diagonal line, we get something which is first order. And then finally, the rate on a steep curve graph changes in unequal amounts, and so the rate concentration graph shows a curved line, and changing the concentration changes the rate squared. So this is a second order reaction. So you can see here, this graph is a lot steeper than this graph. So again, if we plot the rate across this graph here by taking the tangent, and we plot that against concentration of A, and we get a curve upwards, then this is a classic sign of a second order reaction. Like I say, don't get the two confused. Don't get concentration time and rate concentration graphs mixed up. So they're very important, of course they are, but you don't want to get them mixed up because you might interpret them wrong. Okay, so we're going to look at something called rate determining step. Now, rate determining step is the slowest step in a multi-step reaction. Okay, it's quite an interesting one because you might think when you look at reactions that reactions occur in a single step. So in other words, you have your reactants and it produces products, but actually that isn't always the case, and they actually occur via multiple steps. You might form intermediates, for example. So most reactions, like I say, occur via multiple steps, and out of these steps, one of them is the slowest step, and that's the one by speeding that slowest step up, that's the one that's going to have the greatest impact on the overall rate of the reaction. So if we can do something with the slowest step, we have a bit more of an impact. So I like to liken it to making a Victoria sponge because I like bacon. So I'm going to use a lot of bacon analogies here. So let's look at how we make a Victoria sponge. So this can be seen from a multi-step process. So step 1 is we gather the ingredients. That takes about 10 minutes to get everything ready and get everything prepared. Then it takes about 5 minutes to mix the ingredients. Then once we've mixed them, we need to then put it into the tin, bake it in the oven and allow it to cool. That takes 1 hour and 30, so it takes a long time to do that one. And then the final step is we dust with icing and we put the filling in. That's about 5 minutes. So you can see there's a multi-step process. We don't take ingredients and get cake. We have to do something with the ingredients, bake them, dress them, etc. And so this is the multi-step process, a multi-step reaction. So if we bring this across, and we can see that the total time it takes to make this is 1 hour and 50 minutes to make this. So the rate determining step here, the one which is slowing everything down, is step 3. So what we can do, if we were to look into think, okay, how can we make this cake quicker because it's so delicious? How do we make this cake quicker? Well, then what we need to do is we either use a fan oven, and that may take less time for it to cook, or once it has been cooked, to cool it down, we put it in the fridge, and that means it'll cool down quicker. Now that's going to have a much bigger impact on rate of reaction than altering any of the other steps on there. So as a scientist, come back to the chemical world, as a scientist, as a chemist, that's quite useful, because it means if we can identify what the slowest step is, could we do something about that to dramatically speed up the rate of reaction? So, like I say, in chemical reactions, we can use, to speed up the reaction, we could use a catalyst, we could use temperature, for example, heating it up, will help to speed up the rate of reaction as well. So there's various ways in chemistry where we can actually speed up the rate determining step, and hence the overall rate of reaction. So the rate equation, so reactants that appear in the rate equation reactants that appear in the rate equation affect the rate of reaction. So we know that already. So we know that whatever appears in the rate equation, that must have an impact on the rate of reaction, because we'd seen anything that was zero order didn't actually appear in the rate equation. So these reactants or substances derived from them, so if they're made from that, they must appear in the rate determining step. Very important. Okay, substances not in the rate equation won't be in the rate determining step. Okay, so anything that isn't in there, that won't appear in there. So that's the golden rule. Make sure you remember that. Okay, it's not just reactants as well that can appear in the rate equation. Catalysts can too. So just because you might have a rate equation, it might have a species in there which isn't a reactant. You might notice it. If it's say if species C is in the rate equation, but C isn't a reactant, then C must be a catalyst. Okay, so catalysts can appear in the rate equation because they do have an impact on the rate, obviously the rate of reaction. Okay, so the rate equation, this can be found from a multi-step reaction. So let's have a look at this generic reaction here. So you can see here we've got A plus B will give 2C, and that's a fast step. Step 2 is 2C will produce D, that's a slow step, and then D plus E will give F plus G, that's a fast step. So the overall reaction is A plus B plus E will give F plus G. So first, we know that the rate determining step is step 2, as this is the slowest step. Okay, so we've been told that it's a slow step. So one of the reactants is C. We can see that there. So this must appear in the rate equation. Remember, if it's in the rate equation, so the rate equation has your elements that affect rate. So if it's in the rate determining step, then it must be in the rate equation. So notice we've got a 2 next to it. This tells us the power is 2. In other words, it's second order with respect to C. How cool is that? So just by looking at the number in front of the element, we can help to, in a multi-step reaction, we can help to work out the order of it. And we know it's second order with respect to C. So C is an intermediate because it's actually derived from A and B. We wouldn't have C without A and B. So for this reason, both A and B must be in the rate equation too, okay, because it's derived from it. So there's only one of A and one of B, so they're first order with respect to A and B. So the rate equation is pretty simple. It's just A, B, C squared. Okay, so first order with respect to A, first order with respect to B, second order with respect to C. So the rate equation is simply worked out from there. So it's not too bad, as you can see. So remember, though, this is what I was saying before, that actually C doesn't appear in that initial equation. You can see there, C doesn't appear here, doesn't appear in the overall equation. So C must be a catalyst. So this reaction is an example of autocatalysis. You'll see this later on in chemistry, so in the transition metals area of chemistry. Okay, so the rate determining step can be found from the rate equation as well. So this time we're going to do it backwards. So we're going to look at deduce the rate equation from the following reaction step. Obviously this is not generic, this is a specific example. But we've got NO plus NO will give N2O2, and then N2O2 plus O2 will give 2NO2. So the rate equation is rate equals K, NO squared, and O2. So you can see here, this is the overall rate equation that we've been given. So we've been given this, but notice we don't know which one is fast and which one's slow. We have to identify that. So the first thing you'll notice is the ratio of molecules we are looking for. So we're looking for 2 NO and 1 O2. Okay, because it's telling us here, so the rate equation must be NO squared and O2, so that's what we're looking for. So we need to look at the reaction steps here and try and look for a step which has 2 lots of NO and an O2. Well, none of them do. Okay, so none of them have this exact ratio here. So this is where we're going to play some chemical bingo. No, it is very similar to bingo. That's why I thought it looked like bingo. So we need to start from step 1, and basically what we're going to do is we're going to score off the molecules or atoms needed to match the ratio in the rate equation, and then we stop when we've accounted for them all. All right. So and this will be the rate determining step if we've accounted them, and then you shout bingo. No, not really. Okay, so very straightforward, actually. It looks horrendously complicated, but it's not. So, first of all, step 1, we have 2 lots of NO, okay? So, we need to score them off, but we still have an oxygen to get. So, we need to continue to step 2. So, let's score them off now. There we are. Okay, so we've ticked that one off. So, we need an oxygen, so we need to keep going. So, step 2, we have the oxygen molecule in this step. So we've accounted for all the molecules in the rate equation, so we stop and it's shout bingo. Okay? Just shout chemistry bingo, or just chemistry, or yay, or whatever you want to say. So we've cancelled them all off, as you can see. So that means our rate determining step must be step 2, because it's in that step that we've scored off all the elements in our rate determining, in our rate equation. Okay? So it's fairly straightforward. Okay? So the rate mechanism can also be found from the rate determining step. So this is an interesting one. So the following reaction, this one here, can occur via 2 potential mechanisms. Okay, so it can occur via mechanism 1, which is just all in one step. So that's obviously the rate determining step, because there is only one of them. Or it can occur via a 2-step mechanism, where we have a slow step to start with and we have a fast step towards the bottom. So the rate equation is found to be rate equals K, and it's the concentration of our tertiary halogenoalkane or haloalkane, which is this here. And so we need to work out, using this, which mechanism is likely to be correct. Now there's a few reasons or explanations why these ones are slow and fast. So the first one, just to note that the first one is slow, because the strong CBr bond has been broken here. So this is why this is a slow process. And this one's a fast process because there's a good chance of collision, because there's loads of OH minus ions floating around. So this is why it's fast. There's a good chance of them colliding. Okay, so what we need to do is the rate equation tells us that only the tertiary halogenoalkane or haloalkane can actually appear in the rate determining step. So that's the only one that can appear there. So mechanism 1 shows the tertiary halogenoalkane and the OH minus, so that actually shows both of them there. Whereas mechanism 2 only shows the tertiary halogenoalkane, which is this one here. So step 1 does match exactly the rate equation that we've got written down here. So actually what we can say, we can be confident that the reaction mechanism is likely to proceed via mechanism 2 because that has a step in there which exactly matches the rate expression. So how easy is that? Really straightforward. So, dead easy. Pick up the mark, have a look, write down your answer, move on. Okay, dead easy. No real working out here. It's just looking. You just need to know what you're looking for with these types of reactions. Okay, so just coming on to the last section towards the end of the video, and we're going to look at the Arrhenius equation. That's why. I think I might have blown that one. I was going to say, why are pirates so good at chemistry? Because they like the Arrhenius equation. Arrhenius, anyway. Right, next. So the Arrhenius equation links the activation energy and temperature. Honestly, my jokes are terrible. I don't think it was even a joke, to be honest. The Arrhenius equation links activation energy and temperature to the rate constant, which is K. So here is the Arrhenius equation. It looks absolutely horrendous. So we've got all these different parts here, and we're going to look at some of them you've seen, some of you will not have seen. Okay. So the first one is the rate constant, which is K. Okay, we've seen that one before. The Arrhenius constant is new. This is given the letter A. And for the mathematicians out there, you might know this, but the E means exponential, and you'll see a button on your calculator that has an EX button on your calculator. Minus EA is your activation energy, so we've seen that before. R is the gas constant. You would have seen that in the ideal gas equation, PV equals nRT. And T is obviously temperature, that's in Kelvin. So these are the different parts of the Arrhenius equation. So the first important point to note from this equation is that as the activation energy, EA, gets smaller, the rate constant, K, gets bigger. Okay, so the lower the activation energy, the larger the rate constant. Obviously, if we're lowering the activation energy, it means we've got a higher chance of a successful collision. Okay, so this is obviously the reason. So activation energy drops, the rate of reaction increases because you've got more particles that are able to collide with sufficient energy. Okay, so that's very important. And the second important point is that as we increase the temperature, the rate constant K increases. Again, this kind of makes sense because if we've got a higher temperature, the particles have got more kinetic energy. And so this means they're more likely to collide at least with the energy of the activation energy. And as a result, the rate of reaction actually increases as a consequence. Okay. So what we're going to do is we're going to look at the calculations using the Arrhenius equation, okay? Because this is where most of your marks is going to come into actually calculating it, using it. So the Arrhenius equation is great for calculating the activation energy or the rate constant. So, for example, let's look at this specific example here. So calculate the activation energy in kilojoules per mole of a reaction at 330 Kelvin and a rate constant of 1.3 times by 10 to the minus 4 per second. And we're going to assume that the Arrhenius constant is 4.55 times by 10 to the 13 and the gas constant is 8.31. Wow, there's a lot of information there. Right, so let's try and break it down. Again, let's be methodical, break it down, try and simplify it as much as we can. So first of all, what we're going to do is write out the Arrhenius equation. So that's going to be K equals AE minus EA over RT. Okay. So however, what we can do, thankfully, is we can make it a bit simpler and we can take the natural log of both sides and we get rid of that E part, which is probably the scariest bit, let's be honest. So we get rid of that and all we do is take the natural log of both sides. So we do ln K and that equals ln A and then it's just minus EA over RT. There's not a single E, like the small e inside, so that's good. So we've simplified it. Okay. Then what we need to do is then rearrange this thing. Okay. So we need to work out the activation energy, so EA. So we move that to one side of the equation. So EA equals ln A minus ln K. Okay. So we've literally just moved the ER over RT over to one side. And then what we need to do to get EA on its own, we multiply both sides by RT. So this is just rearranging it. Multiply it by RT to get EA on its own. So you can see we've multiplied the left by RT. So we multiply the right by RT. Remember, you might have done this in GCSE maths perhaps. Whatever you do to the left, you must do to the right as well. So if we multiply that by RT, that basically cancels that out. Then we must do the same on the right as well. So now we've got EA on its own. That's great. So now we just need to substitute the numbers in. So we'll need obviously the natural log button, the ln button on your calculator. So then we just put in the figures. So EA equals ln 4.55 times by 10 to the 13 minus ln 1.3 times by 10 to the minus 4. Multiply that by 8.31 and 330. So just put all your numbers in basically. We're going to simplify that a little bit. So we've taken the natural log of all of these numbers here, and so that's what we've simplified it down to. And then you should get an activation energy of 110,781 joules per mole, or 111 kilojoules per mole. Okay. Now I have done a video on this particular example of the Arrhenius equation, looking at the calculations. It's a whiteboard tutorial, so I'll go into a little bit more detail. But just click on the banner there that you can see pop up on your screen, and you'll be able to get access to that. Okay, so we're going to look at Arrhenius plots as well, and we're going to calculate the activation energy from an Arrhenius plot. So the Arrhenius plot can be used to find the activation energy and the Arrhenius constant. So we're going to look at the activation energy example first, and then once we've done that, we're then going to look at how we can calculate the Arrhenius constant. So we can use the same equation, so the simplified one that we've used. So it's the ln k equals ln a minus EA over RT, okay? And then what we can do is we can plot a graph of ln k against 1 over t, and then draw a line of best fit, okay? And then the gradient of that graph actually represents EA over R, so minus EA over R, and then that can be used to work out your activation energy and Arrhenius constant. But like I say, in this slide here, we're going to look at how you calculate the activation energy, then look at Arrhenius constant on the next slide. So here's our graph, and we've plotted our results here. And you can see we've got, just to point out some important points here, we've got ln k on the y-axis here, and we've got 1 over t. This is multiplied times by 10 to the minus 3, these numbers here, just don't forget that. This is on the x-axis. So we're going to work out the activation energy. We've got to work out the gradient, okay? So the gradient is very straightforward. It's change in y over change in x, remember? So the change in y is minus 1.1. Change in x is 0.1 times by 10 to the minus 3. Don't forget to put that bit on because that's what this figure is telling us. So the gradient here is minus 11,000. So EA over R is minus 11,000 for EA over R. But what we need to do is we need to work out just the activation energy because that's what we want to work out. So we need to do a little bit of rearranging. So we move EA to one side of the equation. So we do EA equals minus 11,000 times by 8.31, which is our gas constant. So we put all them in, and we get an activation energy of 91.4 kilojoules per mole. Like I say, I've done a video as well, a whiteboard tutorial video looking at Arrhenius plots as well as the equation. Again, if you just click on the card that appears on the screen, and you'll be able to have a look at that if you wish. Okay, and just sticking on the graph ones as well, the plot ones, this time what we're going to do is, using the same example, we're going to work out the Arrhenius constant instead. So working out the Arrhenius constants, all we do is we substitute the value of the gradient that we've worked out just before and the coordinates of any point on the line into the equation. Okay, so we bring our equation back again. We're using our simplified version with a natural log of both sides. And what I've done is I've rearranged that into the y equals mx plus c coordinates. That's for a straight line graph. Okay, so that is y equals, and then we've got our m, which is the gradient, x, which is the 1 over t bit, so that's the temperature bit, and then plus c is obviously ln a. So we've just rearranged it in there. Now, if you've done, obviously, you would have seen this equation before, y equals mx plus c. So y is obviously the y-axis, it's this value here. X is obviously the x-axis, which is this value here, that's 1 over t. That's this bit. And obviously the m is the gradient, which is EA over R. Okay, and then obviously your C bit is the ln A. So we're just putting the figures in here. So y is ln k, so that's minus 4. which is there. Okay, minus EA over R is the gradient, so that's the information we took from the gradient from the last slide. 1 over T is the coordinate, the x coordinate, and then ln A is the bit that we want to work out. So then we, again, just to break it down a little bit more, still minus 4. We've worked out this bit in the brackets and put it there. That's just from the previous slide. 3.1 times 10 to the minus 3 plus ln A. We then simplify that a little bit further. So we multiply these two numbers to get this. And then we rearrange it to get ln A on its own. So ln A is minus 4 plus 34.1. So we just shuffle that round. So then we work out that ln A is 30.1. But of course, we just want A. We've got the natural log bit on here. So we have to do the exponential button. So that's the shift ln button. And then you'll get the little flashing box just above the E. And you put in that figure there, 30.1. And then you should get your Arrhenius constant value of 1.18 times by 10 to the 13 dm cubed mol to the minus 1 s to the minus 1. And like I say, there are videos. I've done a whiteboard video on Arrhenius plots, so feel free to have a look at that. Okay, and that's it. So that's your lot on rate equations. I bet you're pleased with that. There's a lot of it was a very fast reaction, very fast video, should I say? Oh dear. Right, so this is your that's your video that was done on rate equations. Like I say, there's a full range of videos for AQA for year 1 and year 2. There's a full range there for specifically designed for AQA. I've got some generic whiteboard tutorials as well and some exam walkthroughs. They're all for free. All I ask is you hit the subscribe button just to show your support. That would be fantastic. If you do want access and your own personal copy of these, click on the link below in the description box and you'll be able to purchase them from my test shop. Great value for money. All right, that's it. Okay, bye-bye.